So hi everyone, and welcome to PyData Global 2021. So for your information, this session is recorded. We're going to have a workshop given by Sylvia Lee, which is called Bridging Data and Business, Power Plant Output Optimization based on electricity market price. Sylvia will take questions at some point during the workshop. I'll let her know when she's happy to get questions from the crowd. And the floor is yours.
Right, thank you. So welcome everyone to the workshop. So this is the workshop for Bridging Data and Business. So what we're actually going to go through is how you can set up for the best success going into any sort of data science project around the business context. So we'll be also surrounding this on a use case called for power plant output optimizations. So we'll have the data science part, which is predicting the power plant productions. And then we'll have a kind of business market parts with it, which is using forecast market prices to make decisions on buy and sells. So just a little bit of introduction for myself. I am a data scientist at Integra Data Analytics Solutions. I had a master degree from UBC for the Master of Data Science, and then I've just continue on that path, coming out working with Integra on a lot of different data science projects for our clients, specifically in the oil and gas sectors. And then now we are actually part of Now Vertical. We had the acquisitions not a long time ago, so that's that. So just a little bit of agenda throughout our workshop today. I'll be taking questions pretty much at every single transition point. So I'll be going through a presentation here on machine learning best practices. Best practices as in like when you're dealing with in a business context, not so much of like the actual working of itself, but like inside of best practices to have the best collaborations with your business partners. And then a short introduction on our platform called the Digital Hub that we have built for data science. And then in the transition of this going into the actual use case themselves, I will take some questions. And then, but we'll go through the use case on a Jupyter Notebook and also a little bit of hands-on session, how to build a production grade dashboard on Superset. And then after that, also we can take a more of a Q&A section as well. So just a little bit of introduction of who we are. So Now Vertical, we are a vertically aligned data analytics software and service company whose our sole mission is actually taking a combination of the most advanced automation digital technology and with any sort of deep vertical expertise that we have, combining them to provide the invaluable tools to our clients and customers to make solutions faster and make better data-informed decisions through the diagnostic and predictive and prescriptive model that we can provide. And Integra, now we're part of the Now Vertical umbrella as kind of the lead on the energy sector. So we had years of experience with different consultant projects in the oil and gas sectors. We have provided a lot of solutions that help solve real-world operational challenges using data science and machine learning solutions. And now, because of COVID, we went in and built out a data science platform that actually puts now the power of data science into the hands of our customers. So now going into the part for machine learning best practices with the business and how you can set out for the best success when you're looking to do some data science project with a business partner. So we have come down to two very key points from our years of doing consultant projects and just communicating with our clients. Two very, very important points that actually set you out for success. So the first point is you always want to keep in mind of what is most important. Data science is called data science because data is the most important part of it. A lot of times people get carried away with buzzwords like AI, machine learning, deep learning, and then they kind of lose sight of what is most important. So we always want to make our models and solutions work best for the data. The ultimate goal is to get insight out of the data, but not the other way around. So the model really only performs as good as the data you give it. So whenever we communicate that across to our clients, always be prepared to make it clear to them that spending time and efforts on the data itself is ultimately what's going to give you success down the road. So be prepared to allocate time to just do data cleaning, wrangling, feature engineering, data transformation, anything, you name it, data. The second point of it is also very important, is know exactly what your objective is. A lot of times when you go into a client, they have a very big picture of what the business problem is. And there's so many things that they want to solve. It is a very big landscape that they want to try to tackle. But for you to get the best success out of it is you actually want to pinpoint exactly where the pain points are. You want to find a problem that when solving it, it helps them with a pain point that's painful enough to justify values in your solution. But at the same time, that problem might actually be a fairly simple data science problem that you can actually finish and give results to within a short frame of time. So just pinpointing a very small, simple, but valuable problem, and then having that, it's like building a sandcastle. You have that one sand, and eventually you can build the entire sandcastle, just building on top of the small problem, and eventually maybe solving the entire business problem that they have. So that was just two key oversights. And now, in terms of setting yourself up for success, now you're in this business partnership. We have defined that 4 big sections or categories that we usually go in and explore with our subject matter experts to ensure that everyone is aligned with what the objectives are and know where we're going. So first off, the data. You want to know exactly what your data is. You want to communicate very closely at this point with your subject matter experts to make sure that you're in line with what they understand about the data and what you understand about the data. And a lot of times during this conversation, what you actually find out are gaps inside the data. And those gaps might actually transform into the objective itself. The second part of it is know the nature of your problem. Once you have an idea of what kind of problem you're tackling, is it a classification problem? Is it a clustering problem? What is the key metrics that is going to be what you're using to measure the performance of your model? So this is in terms of help the data scientists on that end to know where you're going eventually in that model building process. The third section that we have here that I think sometimes people don't put enough attention to is the ethical implications. So you actually want to know exactly in every step of the process, from data collections to data cleaning to model building and the final presentation of your business outcome or your predictions and results. What are the ethical implications in every single step of it? You want to make sure that you're not stepping into any problems with ethical implications and concerns here. The last part, envisioning the final product. Very often, just the list of numbers that you get from a prediction model, that's not your final result that you're going to present to them. They're looking for something like a dashboard or a report. The model that you're building actually is not going to be run on a Jupyter notebook or a local script. It's going to be somewhere up deployed in the cloud or on their on-premise software. So you want to know exactly where your model is going and where your result is going. And in terms of that, sometimes those knowing that actually plays a part into when you're deciding what models you want to build. If computation is going to be a bottleneck, maybe deep learning is not a good idea. So having to know that every single these 4 sections, knowing exactly where you're going, that set out you for success. And you're actually in line, your business partner knows where you're going, and just avoids a lot of confusions and assumptions down the road. Now, the iterative process itself in terms of building that data science models, or when you're doing any sort of machine learning projects, I guess as data scientists, we know the steps, we know how to go through it, but this is kind of the way that we have organized it in a way so we can communicate it efficiently with our business partner so that they know exactly where we are. So with the exploration stage, this is the data exploration, you're defining the objective, you're doing your exploratory analysis, you're communicating with your subject matter experts. So then actually what you find out about your data might actually define your objective, shift it, or even like change the directions completely. So in this exploration stage, you're defining the objective, you're pinpointing the problem exactly according to how the data is looking like. Then we go into the model building process, which is another little iterative process of itself. So this is where I guess the data scientist, the data analyst comes in. We work on the data, we transform the data, do feature engineering, we do the model optimizations, tune our model, hyperparameter tuning, and maybe go through a few models, go through a few sets of transformation pipelines, and eventually come up with the best model that we got, given the time frame that we have. And then once you have that model with the minimal viable product or the MVP, then you can start taking that model to the model growth phase. So this is the part where you might actually launch up the model into a bit of a production environment where you can actually start seeing how the model performs in real life with real-time data coming in. And eventually take those new data, retrain your model, make your model better, and deploy again. So there's a little iterative process in itself. And very often the model growth phase is actually where it gets the most excitement. That's also the same attraction that comes in with AI and machine learning, is because the model can grow. It's not like a static model that just stays there in time and just doesn't evolve with the way it changes. So that was just a very quick setting stage on some of the things that we have learned from past experience working with our business partner and in terms of building data science projects. So throughout our time on here, when COVID hits, we have a little bit of data science platform internally. We decided to bring it out with a UI, so it's available to the public. So just a little bit on Digital Hub. This is the data science platform that we have built. What we were noticing is that there was a bit of a lack between a data science development and business intelligence. So then we have built out the platform that hosts the most advanced open source development, visualization, and alerting applications in the cloud environment. And then the overall aim of this is that everything is pre-configured, integrated, and ready to be used. So then you can spend less time on setting things up and configuring and more time targeting and working on the problem itself. So we have also wanted to be a friendly, collaborative environment. So there's a lot of team working kind of capabilities integrated to different parts of the platform on here. And we have three main features that we have. So one is out of the box, everything's pre-configured and ready to use. Cost effective, because you're able to actually manage all of these applications, your dashboard, your business intelligence dashboards, your Jupyter Lab development environment. You can choose to start and stop those runtimes, so manage your costs efficiently that way. And we also have some expert notebooks and template notebooks inside our Jupyter Lab environments that helps guide you along the process and do a little bit of tutorial and just let you know how to deal with a problem when you get one. So just a little bit of overview. I'll be also just going onto the dashboard, the platform itself, and show you a little bit more in the later part of this workshop when we get into the use case. But just a brief introduction, what you will see on the platform is project. So a project is the key organization units that we have on Digital Hub. Every single project, they are a separate entity in that they contain independent applications, storage files, database. All of these applications, they are integrated and installed within minutes when you start a project. They're integrated with the database, they are connected with the file storage, and they are accessible with single sign-on. And of course, with every single project, you have all the users that goes into the project that you can assign to different projects. These users, you can give them actually a role-based user access that actually just automatically get propagated into all of the applications within that project. And then one of the main key features that we have on these projects is data flow. So we wanted to streamline the data flow as much as possible. So what it actually might look like is that we have a Jupyter Lab environment, which you can see in kind of the schematic here on the left here. We would have a Jupyter environments that serve as the core central development environment during the data science project. And then this Jupyter environment, you can actually have it once your data is ready to go, push it into the different databases that's associated to different projects and go inside the dashboarding applications inside, say, project A. It's already automatically integrated with that database. So I can just simply push my data into the database, navigate over to my dashboarding application and start working on my dashboard. So there's no more integrations in between. Everything is streamlined and ready to go. So Jupyter Lab itself, it's an open source platform. Everyone can get access to it. What's special about Jupyter Lab on our Digital Hub here is that we have already customized it for data science. So we've pre-installed it with a lot of the popular language kernels, along with the most popular data science libraries that you often use with these languages, so Python and R. We have a shared folder for team collaborations. So every single project on the Digital Hub here, you can see a shared folder within the Jupyter Lab in which all of your members, when they launch up into their Jupyter Lab instance, have access to. So all those files are synchronized just to streamline that team collaboration process. We have, again, as I mentioned, the notebook templates on real-world oil and gas use cases. So just some of the use case and some of the techniques in guiding you how to approach a problem, say if it's a time series analysis or a machine learning analysis. And also, lastly, we have it pre-installed with some of the most popular data science extensions inside the Jupyter Lab environment here. So your Conda, you manage different environments, Git for version control, and JupyText, which is a nice extension for doing conversions between notebook and script, and a lot more others, but here's a few examples. Then we have these open source business analytics and visualization applications. So Superset, very popular for BI purposes, building very, very nice dashboards that then you can just do click and drop when you're building the dashboard. We'll be also going through it a little bit at the end of the workshop here, just showcasing a dashboard on Superset and how you can build that dashboard with the prediction results that we have from our use case. And Grafana, which is a very popular time series dashboard, optimized for time series visualizations, and actually do exceptions reporting and monitoring and alerts. So just another few key points on here. So with the Digital Hub platform, we want to make it easiest for you when you do governance, team management, and cost control. So again, with team settings, just add invites people into different projects. And then in terms of cost control, you can always choose to start it, launch, and post in applications. Just need it to run based on the need. So if all that blurb about Digital Hub makes you slightly interested in Digital Hub, feel free to come on to cloud.digitalhub.io on here, and then you can register an account. We have a few plans that is available in academia, individual, and teams plan. So feel free to go in and subscribe to the plan, and then just create a project and explore away. So now we can actually go into the use case itself that I'll be talking to a little bit more about. But at this point, because we're going to dive deep into the use case and go into Jupyter Notebook and do all the hands-on section, is there any questions at this point that you can answer?
There is none in the chat, so if no one talks, you can go on.
Okay, that's good. Okay, so going into the use case itself, this use case is on the electrical power output. And this is what actually becomes very important is the accurate predictions of these power outputs. They become very important in making economical and operation decisions. And if you have the right buy and sell decisions according to how your electrical plant is performing, you can actually save millions of dollars. So in this hands-on section, what we're going to do is that it's a little bit of a two-part process. So we're going to go through first the data science part of it, doing the energy production prediction with a data science model. And then the second part of it will be a market analysis. So how we take that predictions, plug it in with a forecast price forecast market price for electrical energies, and then come up with a recommended market action. So because everything in here, really this workshop is all about processes, it's key to note that we'll just be doing a very general guide tutorial through how that entire data science process look like. Really every single part of that stage there, data exploration, feature engineering, machine learning model building, those deserve a workshop of its own. But you can kind of think of it as kind of this workshop, and what we outlined here is how you can bring all of these processes together into one big picture. So with that, I'm going to navigate over to my browser here. Before we go into the notebook, I'll actually just show you a little bit on the platform here. I might have to log in again. Yes, I do. So this, you can come into the platform through cloud.digitalhub.io and then sign up for an account here. You can click on there, but I'm just gonna log in. So this is how our digital hub looks like. You will have a homepage where we have some resources, some past tutorials and webinars we've done ourselves, and then some blogs if you're interested in. You can see in my projects here, I already have several projects going on with different sort of analysis. Particularly this one will be looking at power plant energy predictions. But before you can go on to and create any project, you will need a subscription with us, which you can just navigate to and explore a little bit more in the pricing page here. Either try out to get the linear plan for free, or you can also contact us for a demo on the platform if you're interested in itself. But this is just a very quick look at what the platform looks like. So you can see on here, if I navigate to my project, I have a superset and a Grafana instance, and also my Jupyter Lab that is running right now. Right now, I don't have my superset running, but I'm just gonna launch it up right now so it's ready to go once we're done with the notebook. So I'm gonna go through the notebook on here. Sorry. So the notebook, I have a GitHub repository that contains the notebook and the data sets in here. And also there is a quick PDF document for the latter part of the workshop where we are going to go into supersets and actually building that production dashboard. So this link is already inside the Slack channel. So if you're inside the Slack channel in the PyData, it's already there. Feel free to go in and just pull the repository and then just follow along the notebook as well. But for time purpose and this webinar, I already pre-run the notebook so that we can go through the notebook smoothly. Okay, so if I said this is the problem domain is in the electrical generations of a combined cycle power plant. So I have taken a open data set from UCI machine learning repository for the power plant data. And then what I have taken for the market analysis part of it is a pool price of the electrical market prices forecast data from AESO, which is the Alberta Electrical Service Operators. Because we're in Alberta, also we're in Canada in here. Alberta is the province that we're in. So this is kind of like the official place where we have all of those electrical market data. So we can go through the notebook, see a little bit of the required libraries in here. I've pulled out the table of content on the side here so you can follow along at which step we are at for the notebook. So again, every single part of these sections in here deserve a very good workshop of its own, really. But in this case, we're just gonna really present the ideas of what happens in every single step here. So you have a big general idea of when you approach a data science project, what's kind of the process that looks like. So first off, when I get the data, of course, the first thing you're gonna do is explore out the data. You want to know how big of a data you're working with and what are the features you're working with, and if there are any problem inside the data, as a matter of fact. So if I just pull out the energy, the electrical plant data in here, I can see that I have about 9,568 data points that is collected from that power plant over 6 years when it was working in full force. Some of the variables that I have in here is temperature on an hourly basis, temperature, the exhaust vacuum pressure, the ambient pressure, and the relative humidity. And of course, then we have the record of the hourly energy output of that hour for that plant. So in this case, with the prediction problem that we're going with, this is obviously a supervised learning problem where we already have our predicting variable in here, and then the rest of these environment related data is going to be our predictors. So for a EDA analysis on here, I am using a package called Pandas Profiling, which is a very neat package that you can install. And then what it actually does is that once you have given a data set, it provides you a very nice interface with doing a lot of the basic summary statistic analysis for you. So right away, I can see the number of observations, so the number, how big of the data I'm working with, the number of features that I have, how many of them are numerical, how many is categorical, if I have any missing cells, do I have any duplicate rows. It's a very nice summary on here. I can also go into different variables in here and just take a look at every single one of them. What are the summary statistics that's returning, and also the distributions of it. So looking through my variables here, there's not too much of an outlier problem. There's also no missing data problem, which is very nice for a data set. This is usually kind of the stage of the data of how you want it to look like by the end of the data wrangling. There's maybe a little bit of problem in terms of normality of my variables in here, but that just exists of the data itself. Nice part is you can also look at interactions, to the interactions of your different variables on here, look at how they look like. If you want to see just a correlation heat map, that's also available inside this widget here. It's a very nice widget for you to look at. But overall, just scrolling through the data sets there, I see that there's no really significant need for any more data wrangling. This is probably assuming that it's already done. There's no really any outliers or any missing data in my data set. So I can just really go on forward with the next part of my analysis there. Though I did notice there's a bit of high correlations between my features that might become a problem later on in model building for these intercorrelations. But that's just something to keep in mind. So the next set of data that I'm looking at is the market data. So the pool price forecast data that I got from AESO, took it from the time, which is the exact same time frame that I have with my energy data. So what it's showing is the forecast pool price, the actual price of that the energy during that hour, day ahead forecast for the internal loads and the difference. But really we'll just be using the forecast pool price for our analysis there. These forecast pool price, they were made 2 hours in advance to when the price is actually posted. So for every single time, for every single hour, you will have the forecast for the next 2 hours. That's how it works on the AESO there. A little bit of parsing on the date time just because the date variable that is returned from the extract of that data there is not parsable by pandas, by Python. So there's a little bit of data wrangling for the datetime variable there in here. So is there any questions about the data at this point? If not, I will continue on forward. I don't think I see anything in the chat, so I'll just keep on going. So the next part that you would do anyway with the coming into any data machine learning process is you want to split up your data. In general, how that looks like is for what you would want to do is that you want to hold out a portion of your data that you won't touch until the very, 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 very end. Because what this is coming into is that you want to make sure that the model that you have by the end of the process is going to be able to generalize. So this is coming into the problem for optimization bias and overfitting. Sometimes you use the data so much and retraining the model so much, getting to a point where you see a very nice accuracy or a very nice metric on your performance. But in the end, maybe that model is just performing very well on your training set of data. And once you generalize it to data that you haven't seen before, that's where it's gonna go wrong. So that's also known as the golden rule. A general practice might be to split up it into a training set that's about 60%, testing set 20%, validation, which is the holdout set, to be 20%. But for this notebook, we're going to use a concept called cross validations, in which so then I would just split up my data set into 80% for my working data, and then the last 20% as my validation holdout set. So in case you're not familiar with the concept of cross-fold validations, there is a little blurb in here just showing you what that looks like. So in general, what this is trying to do is to bring out the most from the data. So pretty much you can think of it as every single observations that you have in your data set is eventually once going to serve as the training set in training your model, and serve once as the validation or testing set in testing out your model. for the performance metric. So there's a nice little diagram in here that shows you how that will work. So in this case, we're splitting the data that we're working with. So this will be my 80% data, not the 20% holdout, just the 80%. We're splitting that 80% again into 5 different sections. And then for each section, we're going to perform a model building and a model evaluations. So then in the first time, I might take out the first section as kind of my test set. So that is where I do my model evaluation, while the rest of the 4 sections will be used for training the model. And then the next round, I'm going to use the second portion as testing and the rest of it as training, and third round, so on and so forth. And eventually your final performance metric is going to be an average of the evaluation performance metric from each of these iterations that you did in your cross-code validations. So this is really just a way for us to be able to really use the most out of the data that we have. This is especially useful if your data set is relatively small, in which maybe holding out 20% already for validation and just taking 60% of your data for training and 20% for testing. That also can come into a lot with might step into some loophole with the bias variance trade-offs and also the overfitting there. You can, so then we'll be using cross validations as we go on forward with Notebook here. So for every, wherever we do a hyperparameter tuning, we have to retest and retrain our model, we'll be using the cross-code validations. So let's say I split up my data here. So you can kind of look at how it looks like. So I did 80% of my data. So that's really now a training size of about 7,800 observations. And then my validation set for about 20%. And because we have that last part of the forecast analysis, I've reserved out about 1 week's worth of time at the end of the data sets there for that market analysis. So in this case, how I split up my training and the validation set is I just took the last 3 months as my validation set, and then the first part of it as my training set. So this is kind of imitating the model where your model is built on past data and then it has to predict on future data. So this is just for this case, it makes sense. In some other problems, it might actually make more sense if you shuffle up your data. So then you take a random portion, a random subset of 80% as your training size, and then random subset of validations as your validation size. That's pretty dependent on the problem. So the next part, we have to split up our data. We finished cleaning it. We finished wrangling it. We did a bit of data exploration analysis now. Now we're gonna do a little bit of feature engineering. So from my initial exploration of my data, I already know that I have some numerical variable that I'm working with. There's some categorical variable that I'm working with. In terms of specifically just for the data in there. So then like now I can do a little bit more feature engineering. So this is the feature transformations, any sort of imputations, outliers handling, binning, feature splitting, feature aggregations of those. I have also linked a recommended read here for some of the fundamental techniques of feature engineering if you want to go and read a little bit more about it. So it's very important to know that what transformation engineering technique suits well for your data. In this data set, we don't have any outliers. We don't really have any missing data, which is nice. But most of the features have some large ranges. So then we might consider doing some sort of log transformations on it. And in terms of this, when deciding what sort of feature engineering you do, specifically, you have to know what works best for your data set. So the numerical variables, the ranges of those numerical variables versus categorical variables. And also the model that you're considering training. So some models, they might actually work very nicely with some transformations, like KNN being a distance-based model might work very well when you apply log transformations to a numerical variable versus applying log transformations on your numerical variables might not make much of a difference when you're using a decision tree, which would actually show a little bit more down this notebook here. And just one very key important thing to keep in mind that I have seen people fall very commonly mistakes into is that whatever transformations that you're applying to your training set, you want to do the exact transformation on your validation set. So just a quick example in here, say I'm doing normalizations for my ambient pressure in here. So for normalizations, we need to know the minimum value inside for this feature and the maximum value for this feature. Those are two parameters that we need to apply normalizations. So I have the min and max here for my training set, which is 903 to 1033. So in this case, when I apply this transformation on my validation set, I am using the same maximum that I have for my training set, not the maximum that I have for my validation set. So this is just a common thing that is easy to fall into when you're doing feature transformations.
There are two questions in the chat. Do you want to take them now or?
Oh, sure. Actually, I'll just finish maybe this last part here in feature engineering, and then I'll answer the questions. Yeah. Okay. So I just did a quick code in here. I coded up a class object for doing the transformation pipeline, just to showcase a little bit in terms of if you know a little bit of coding, you can read through it to see how that feature engineering is kind of works out in the backend. So how it tracks all the parameters, how it tracks the different types of feature engineering techniques that you're going through, and then transform the features for you. So this is just for demonstration purpose. A lot of time when we're actually working on the data science problem, there is a lot of machine learning packages out there like scikit-learn that already provide a lot of powerful engineering functions for you. But this is just for demonstration purpose that you can look through and get a good understanding on how the feature transformation looks like. So in here, I can show I have applied that transformation pipeline that I have on my training sets. So I fitted and transformed my training set in here. You can see from the code here. And then I simply just transformed my validation set with the same pipeline. So I didn't refit the transformation pipeline for a validation set. You simply just use the same fitted pipeline and then transform your validation sets there, just re-emphasizing that point. Okay. So that was feature engineering. Now we will go a little bit more into machine learning model building. And I'll also take a look at the chat here for the questions.
Yeah, so first question was, how correlated are data points that are next to each other? Have you tried temporal cross-validation? So it was a bit earlier.
Okay. Then, okay. So with the data set next to each other, so I didn't do temporal cross-validations at this point with the data set I had on there, because from my pandas profiling, I think at that point, what I saw on there was that there is actually very high correlations between the energy output and some of the variables already. So like temperature and humidity. So in that case, for me, actually at that point, I was thinking I would do a regression analysis more than a machine learning model. But in that case, I didn't do temporal cross-validation, but that would be very interesting to look at as well. So that is definitely a good point to do as well. And plus for the temporal cross-validations, if you look into the actual data sets from the UCI machine learning repository, there's no time on there. We added in the date time ourselves for the purpose of this demonstration.
And the second question is about the data. Why is ambient pressure an interesting variable?
Did that came out when we were talking about feature engineering, or it's just in general? So the ambient pressure, it's definitely a important feature in terms of how the power plant works. So the ambient pressure of that power plant, it affects quite quite significantly in terms of the amount of energy you can output during that hour, and from just the way the energy plant works. In terms of why I'm using ambient pressure as kind of the example here for the transformations, I kind of just chose ambient pressure because it started with an A. But if you look through the transformations pipeline in here, and then at the end, I applied the transformations for the ambient pressure. And actually, I did pretty much the same transformations for relative humidity and the exhaust vacuum and relative humidity. So Oh, and temperature, sorry. So then like, because these are all numerical variables, I want to apply some sort of normalization or standardizations to them. So I don't know if that was the question. But yeah. Okay. So maybe a little bit more on like the transformation. So what I decided to do again was just doing standardization, normalizations on these numerical variables here. And then for my date time, instead of just having it as a date time variable, I extract out the month of the time. And then also doing just in terms of the day, it's kind of grouped it into, was it in the beginning of the month? So like the first 10 days, middle of the month, or the end of the month. And then put it out with one hot encoding and dealing with kind of transforming it into more like a categorical variable. So now going into the machine learning model building itself, I'm going to look at two basic machine learning models. So we have the support vector regressor and also the decision tree regressor. So these are the regression version of SVM and decision trees classifications. And then but in this case, we're doing a regression for the problem here. So the support vector model, again, is a distance-based algorithm. So you're gonna see a big difference when we apply standardization and normalizations on our numerical features versus when we didn't transform our features, whereas in the decision tree, we'll be less dependent on these type of transformations. If you want to learn more about different machine learning models, the scikit-learn user guide actually provides very good references to how all these different machine learning models work. And also there is a very nice blog article here by Terence Shin that actually introduces quite well the basics of the machine learning models. So you can see in here, I have applied the support vector model and the decision tree model on both the transformed data and the untransformed data. So this is just prior to redoing any sort of hyperparameter tuning. I'm just using the default state, default configurations from the scikit-learn machine learning packages. And then doing cross-validations on the data set when they are transformed and the data set when they're not transformed. In the case when they're not transformed, because we can't really deal with date time variables, I just simply dropped the date time variables on those. So with the transformation scores on here, you can see that with a SVR machine learning model, you can see there's a very big difference. So then once we have transformed the data, applied that standardization transformation, we have about 0.92 with our validation score. When we didn't transform it, we were at about 0.3. In contrast, when we applied it to a decision tree regressor, the difference isn't that big, 0.917 versus 0.921. The difference in there is not huge. So this is just a score summary in here. You can see that like the SVR model and the decision model, if I round it up, the best it went was 0.92 on the data set there. And then when we didn't transform it on the SVR model, just significantly worse. So from here, because for demonstration purpose only, if you look into all those little scores at the end, the SVR model after on the transformed data gave us the best score in this case. So we're just going to use the SVR model as we go on forward with the hyperparameter tuning. Now, usually on the real life situations, we would actually still go on forward with a decision tree model, just because maybe after your hyperparameter on the decision tree, it would work a lot better. But this is just for demonstration purpose only that we just decide to go with the SVR model for the rest of the notebook. So feature engineering was working on the features and working on the data. Hyperparameter tuning is working on the model. So in terms of hyperparameter tuning, there's a little bit blurb on here, and then also a nice quote and a blog in here explaining a little bit more in depth what hyperparameter tuning is. But eventually, in general, what happens for every single model, machine learning model that you decide to go with, there is parameters and then there is hyperparameters. You can think of hyperparameters as kind of like the rules that you give to the model when it's training. to let them know what the parameters should be. And so say for a decision tree, some of the hyperparameter that you might set for the model when it's training is what's the max depth of the tree. So how many times it can make a decision. And also maybe if a feature that you make a decision on, so in a decision stump, can it be used more than once throughout that training process? So these are like rules that you give to the model. And then parameters though, what they are is when the model actually fits to the data set that you have. It's deciding on which feature it's going to use at a particular decision stump, what values to make the decisions on, and what is eventually the depth, the actual depth of the decision tree once it's finished training. So in this case, so setting out the hyperparameters, setting out the right rules for your machine learning model to know what it's working within a scope of, that's going to what's eventually going to affect the performance of the model. So now that's just a little general blurb on hyperparameter tuning. Again, you can read a little bit more on there. There's a few blogs on there that you can go in and read. In this case, we're going to go with SVR model. In general, if you look into the documentations for the SVR model on scikit-learn, there is 3 hyperparameters that we're going to be playing with. So one is the kernel, which is the function that is used to classify and do the regressions on. So these are categorical. So there's linear, poly, RBF, sigmoid. And then there's this C value, which is the regularization parameters. So this control how generalized your model is. And then we also have gamma, which is the kernel coefficient for specifically if you want to go with the RBF, poly, or sigmoid kernel functions. For these ones, you can either give it a numerical variable or you can just set it to auto or scale mode where the gamma is dependent on it. So again, to learn more a little bit in details into what all of these kernels are, you can always go to the scikit-learn user guide. They provide very good references and detailed documentations on there. But now we're actually going to go to the hyperparameter tuning process itself. There are two very general mode in how we do hyperparameter tuning. So there is the grid search, and then there's the randomized search. So a grid search, you give it a list or the limits of the hyperparameters, and then it goes through an exhaustive, goes through the list exhaustively, and then it trains the model and score for every single combination of the hyperparameter tuning. And then we have the randomized search, where instead of giving an exact list or limits of these hyperparameters, you give it a distributions or just a bound of those hyperparameters, and then it just do a very randomized samples of combinations of these hyperparameters and train and tune in those defined spaces. So we're going to go through each of these inside the notebooks just to demonstrate how they look like. So again, with a little bit of pros and cons. With the grid search, you're doing a very exhaustive search of your hyperparameters. So say if you have an important parameter on one hand here and the parameter 2 on the x-axis here, the grid search goes through every single one of it in terms of the exhaustive combinations. Whereas in a randomized search, it's taking a random sample of combinations. So the grid search is going to be very costly on time and computations, where the randomized layer is usually what we would use when we first start out with hyperparameter tuning. So a very common process is usually we start out with randomized layer with the randomized search. Then we can kind of get an idea of what are the bounds and the bounds of the hyperparameter that works best. And then we slowly use that, maybe applying that to randomized search with a smaller bound and smaller bound, and eventually use a grid search to exhaustively search through all of the combinations once you have a very idea of a smaller bound and the smaller set of hyperparameters that you have. So for demonstration purpose only, on here, we're running a very small grid search with just 2. So I gave it the options here for just 2 kernels, 2 C values and 2 gamma values. So doing a grid search, this is a total of 8 different combinations. So what it did is that it trained the model 8 times on each combinations. And because it was a 5-fold cross-validation, so that is total of 40 fits. And then it calculates out what is the best score for you and then what are the best parameters in this case. So then I also ran the grid search a little bit more. You can see from the commented out sections in here on the back end, and just show you a little bit more in terms of how that looks like. Now, again, with the randomized search, so the pros and cons, I think we've mentioned in contrast with the grid search, usually it's better at the very beginning when you're just kind of doing an initial exploration of your hyperparameter space there. In this case, you can see from the difference on there, the kernel, it's still just a list because these are categorical variables for them, so a categorical choice. And then, but for C's and gamma, instead of a list of the values, I gave it a distribution. So this was a log uniform distributions with a range, and then for both C and gamma. And then, so in contrast to grid search, where it already knew that it was doing 8 combinations. In this case, I have to specify to it do 8, so that we can do a fair comparisons between the randomized search and the grid search. So in this case, again, you can get the best score out of your randomized search function here, and then the best parameters comes in. Also did a run of this randomized search with 100 iterations instead of 8. Took about 11 minutes to finish. And then this was the result that it came back. So it did a little bit more of a search in that space and came up with a best score that was slightly better than the ones that we did when we just did 8 iterations. So after something that we would do after exploring, doing some of the grid search here is that we want to explore the hyperparameter space. So you want to limit out to a space of the hyperparameter where you actually get better performance model. So in this case, I already ran I took the randomized search data from when we ran that 100 iterations, and then created a quick visualization on here just to with a few of the hyperparameters. So then this is how it looks like when the kernel was linear, when the kernel was RBF versus kernel when it was poly. And then on the y-axis here, it's a little bit small to see, but it's the gamma. And then on the x-axis is a C value. And then the color of it is the performance of the model. So you can see this is just kind of conceptualizing how you explore kind of like the hyperparameter space. I can see that the model performs pretty well inside the space here, and the space there. So then the next iterations of hyperparameter tuning that I might do is then I'm going to redefine my bounds for those distributions and to just limit it to this space, and this space, do another randomized search and slowly just limit it down, move further and further and further until you get to the best set of hyperparameter that you have for your model. So that's just kind of the process there for hyperparameter tuning. Eventually, so in this case, I'm just going to assume that with this, I'm good enough. I have a hyperparameter model that gave me best a score for 0.93, and that is already good enough for my model. So I'm just going to go ahead and use this best rank score here, and I'm just going to continue on forward now with my model evaluations. Let's check on time. Okay. So with model evaluations, there's a few basic model of how you can actually do evaluations. The most basic evaluations is you just compare the train and test score between your different models. So we have the base model where I was just using just the default SVR from the package there. And then our optimized model now with those hyperparameters that gave us the best scores. So in this case, we can see it went from 0.92 to 0.93, almost 0.94 for the training set. And then we went from 0.90 for the test scores to 0.93 for the test scores on here. But just in case you don't know if this difference going from 0.90 to 0.93 was significant enough to tell you that this optimized model is doing better than the base model, there is always statistical evaluations that you do. So in this case, this is just an example of the Wynne-Cousins rank test. In this case, what it actually does is that it utilizes the feature for cross-validations, because for cross-validations, you have those, say, 5-fold cross-validations, you would have 5 test scores. So then that now becomes kind of the population of sample that you're doing your statistical test on. And then comparing the samples, the 5 samples you have for that base model and the 5 samples that we have from our optimized model, it does a statistical test on it, where the null value is that they are not significantly different from each other. And then of course you have your p-values. In this case, it's smaller than 0.05. So we would conclude that it is significantly different. So in this case, I'm using this test in here. Of course, it's showing a user warning that our sample size is too small, but assuming that this is a valid test, I would say that our hyperparameter tuned optimized model is performing significantly better than our base model. So the last part here now, let's say I'm completely happy with that optimized model that we have with the SVR. Now this is where the holdout validation set comes in. So this is a set, again, it was never used through the entire notebook, except for the transformation part being used in the machine learning model anywhere. So then now I'm going to perform that validation, perform the predictions on the validation set here, and then take the score out of it. So we can see that with the base model validations, 0.92, and then with the optimized model, 0.937. So in this case, because my validation score is not that much different from the score that I had just looking at it with the test scores and the in the above section, in the above cell there. So in this case, our model is actually able to be generalized fairly well on this new set of data in the validation set that it has never seen before. Another common thing to look at your model through is to look at the residuals. So then you want to ensure that your model is not going through any sort of bias. Then looking at the residuals is where I would tell you that. So look, the residuals is the difference between your predicted value and the actual value for your prediction. So your y variable. So in this case, our energy that we're trying to predict. So what you want to see is that you want to see a fairly randomized cluster around 0. So in this case, we have a few outliers, but that doesn't seem like too much of a problem. Where you would see a problem is that if your residuals goes in a very obvious trend, upward, downward, or curve, if you see a very obvious trend, that is where your model is having some sort of bias problem. So that's the residuals part is one way of looking at it. The QQ plot and for the normalized residuals is another way of just visualizing that. So you want to see a very bell-shaped distributions, symmetric normal distributions around 0 for the quantiles. Again, so we have a few outliers, which was the same as we've seen from the graph above. And also for the QQ plot here, you want it to align fairly well with that red line there. Again, we see a little bit tail off because of those outliers. And then the last part, of course, is the most exciting part, is that you actually compare your predicted value with the actual value. So you can, of course, anytime put out the plots together. In this case, I use Plotly so that we can have a little bit more interactions with it. But you can see that the actual and the predicted values and how they, the differences between them to ensure that they're not doing anything too drastically wrong. So that would actually concludes our part for the machine learning model building itself. Is there any questions on that before I move on to the market analysis? We're now bringing in the forecast and dumping that business context on top of it. Is there any questions? I'm looking in chat quickly here.
There is no question in the chat. Oh, maybe one coming. Is the gain using a validation data set?
Okay, so I would say there's not, in terms of gain, I would say more of like the benefits of using a validation data set is that you ensure that your model is not overfitting. So the whole purpose of the validation set is that it is a set of data that your model has not seen before during the entire model building process. What is a common thing that could happen when you're model building, because you're working on that same set of data so much and you're tuning up your validation score, also not validation score, your accuracy score to that data set. What is a common problem is called overfitting. So your model ends up doing very well on that training set, and then it doesn't know what to do when you actually give it things that you haven't seen before, because it's just fitted so well to that set all the way to the little crins and nicks inside the data set that when you give it a set of data you haven't seen before, it can't generalize. So it ends up doing very bad on the validation set. So that's a little overfitting by the test set. No, because the test set is also things that it has seen inside the training process. So we use the test set for us to know, you can think of it in this way. So the test set tells you when you're training a bunch of different models, which model does better than the other. But eventually, once you have selected that model that does the best out of it, then to ensure that that model is not having any overfitting problem, then you apply the validation set over it to let it know, to see how well it generalizes. Because all in all, the test set is also part of that working data that you're working with in the model building process. It has seen that data before. So the whole golden rule is that you have to validate it on data that it hasn't seen before. So let that answers the questions.
So there is another one. Have you seen any cases where underfitting shows up?
Okay. Yes. So underfitting, it's quite popular as well. So in terms of underfitting, so that just indicates to us that your model, again, because machine learning, in a sense, it's a technical process, and in a sense, it's an art. Because when you're doing data science and machine learning, it's all about that balance that you find between bias and variance, overfitting and underfitting, being accurate enough, but also being generalized enough. So it's all about managing that balance. So then in the cases where we have seen underfitting show up, yes, so it performs very well on our data set there, and then it doesn't perform as well on the validation set there. But oftentimes with the underfitting, it also gives you signs when you were just training the model. So then when you're training and your test score doesn't perform as well, that's usually cases of underfitting. And then in this case of how you can fix it, you just have to go back. And so this is actually very common cases. In this case, we were having a very general example where we only have one validation set, but a lot of time in real life, when your data set is big enough, people tend to hold up several parts of the validation set. So we will have validation set 1, set 2, set 3, set 4, set 5. So then once you have, you use the first validation set, you can get insights into whether you're overfitting or underfitting on there. You optimize that part. And then once you get a score that's big enough, then you apply the second set of validations to ensure that whatever you did on top, after you get more insights from the validation set, is actually solving your problem. So then with underfitting, the main solving really is just you do better feature selections, feature engineering. Again, all the process we've talked about here. Maybe it's a problem in your data that your data is not working well for the model that you're training it with, or it might be the model hyperparameter. So maybe there is a space that you missed against with the randomized search because it might just randomly have not go into that space that it performs the best. That is a chance. So then maybe you just have to do another randomized search to make sure that you're getting an idea of that full parameter space and knowing exactly where that good part is. And then with the hyperparameter, another thing that you can mess with is the regularization parameter. So a lot of the machine learning model, there's a regularization parameter that controls the generalized aspect of the machine learning models. So that regularization parameters, or even other regularization techniques that comes on top of the models, is all the things that you can consider when fixing an underfitting problem. Hope that answers it. If there's something else, I'll just go on forward because of time's sake. I just want to get through this market analysis part as well. If you have any more questions about data science and model building, you can always go to the Slack channel after the webinars here, and then I can do a little bit more answering there as well. And I believe my LinkedIn is also on the profile page. So if you want to chat through LinkedIn as well, that's also possible. Okay, so now we have that forecast set of data. So remember that last 1 week set of data that I extracted out of the entire data set for this forecast analysis. So with the, again, so this is how the data set looks like. This is a raw data set. What I'm going to do is that I'm going to transform it with the exact same pipeline that I have. Again, I didn't fit it. I just simply transformed it. And then I I predict model the energy output for this forecast set of data using the model that we had, so that best model that we had, and now I append it to this data set here. So that was just getting the forecasting part of my energy output. So now I'm gonna go in and merge it in with the market data that I got from AESO based on the time values on here. So now I know what I've predicted for that hour, what my energy output is, and AESO has given me a forecast pool price for that hour. So with these two variables, what we can do now is that for a power plant, they always know what their internal loads are. In this case, I don't have the data on that. So I simulated an internal load for that power plant for that hour. And then with some of the reports here from the US EIA, I have the average levelized cost of how much it takes to produce electricity in a combined cycle power plant. So now there's a few things that we have. We know the internal demand, so how much our power plant needs to run. We have our predictions of how much our power plant can produce in that hour. We know the cost of the productions, and we have the forecast pool price of what electricity price looks like in the market at that hour. So with these four things, then we can apply just actually a very simple market logic on top of it. So if my production cost is going to be higher than that price in the market, then I would just buy off my demand from the market because it's cost less that way. But if my production cost is less than the price that is on the market, then there's two scenarios. Either from our prediction of our electricity production, we either have a shortage. So whatever we can produce in that hour is less than our internal demand. In that case, we will produce whatever we have, and then we buy the rest from the market. If we have a surplus, so whatever we can produce is higher than our internal demand, then we will produce as much as we can, and then sell our surplus to the market and get back a little bit of money that way. So this is just a very simple logic applied to a bunch of if-else or where statements with NumPy. So in the end, in here, what I have produced as a result is a set of data sets here that just shows me what's my internal demand at that hour, I call it excess, but it's pretty much the difference between my production and my demand. If it is a shortage or a surplus at that hour, what is the cost if I produce everything? What is the cost if I just buy my demand from the market? Or if I just buy only the shortages from the market? And then what is the price that I can get back if I sell the surplus to the market? And then at the end, what is the recommended actions in terms of are we just producing our costs and buying our shortages, we're producing and then selling the surpluses, or are we just buying our demand from the market? And then eventually we have the net cost after we have applied that market action. So with Jupyter Notebook and using Matplotlib, you can produce some pretty nice visuals already on here with energy. So then in terms of the shortage and surpluses through each hour, so how much was the shortage, how much was the surplus, you can also plot out your net cost on here, and then what are the recommended actions. So these are very nice graphs inside the notebook in here, but ultimately, whenever you present to your market partners, generally, they're not gonna be very appealing to the idea that they have to run a notebook and only see the graphs in the notebook. So this is where now we're going to go into our dashboard and start building that up so that they can open up a nice dashboard and see pretty visuals. But in terms of just a quick part in here, I didn't run this part because I already have ran it, pushing my data into that database that I have for the markets. But then this on our Digital Hub platform on here, how we have, so as I've mentioned, how we streamlined that process for the data flow. What we have actually already done is that when you log into your Jupyter Lab environment, you would already have your URI, so your connection string to your database, inputted as an environmental variable for you. So then with this notebook, and then I can just simply grab that environmental variable from the terminal, or you can just simply replace the power plant energy prediction with the name of your project or in capital, and then just load in my data that way, and then just plug everything in with SQL coming. So this is just a quick note on the notebook on here. And then, yes, yeah, so it is on, yes, so thank you everyone for helping me post the GitHub link onto the chat there. So yes, this notebook and also a set of instructions of what you're going to see on building the dashboard and superset is inside this GitHub repository here. So the notebook is here, PyData notebook, and then the creating energy production, this is going to what you're going to see in this next part here. Okay, so I'm just gonna, so that wraps it up for the notebook. I'm just gonna show you quickly of what happens on the dataset there. So you can see I started my superset instance before we go into the notebook. Now it's ready to go. So I'm just gonna simply go in and launch it up. Okay. So what you're going to see here, I'm just gonna show you what it looks like in general. So this is a dashboard that I have built out based on that market predictions that we have, and also the electricity predictions. So what you can see in here on the dashboard is there's a little bit of a time filter that you can filter for. In this case, because we're using on past data that was a year ago, I didn't have any time filter range on this. But the nice part about this dashboard is that as say you're already in production environment and you're ingesting data into that database on a timely basis, you can set out the time filter on here. The dashboard get updated real time as soon as those data are inside the database. So here's just something that I put together that makes it easier to show and give values, actually the business value. This is where the business outcome comes in, is that the operators or the decision maker can ultimately see that the total estimated cost, if we follow the recommendations that is offered by the engine there, is about 2.5 billion. This is only a week's worth of time, by the way. And if estimated, if we just buy everything from the market, which is about 4 million, you're already saving 2 million in that 1 week. Versus if you don't care about anything and just estimate to full production regardlessly, in this case, you're gonna have a few shortages here and there without buying anything from the market, you're still saving about 0.1 million. So about 100,000 there. So, and the estimated total energy production in that week is about 72,000 megawatts. So then we have a little bit of chart in here. You can see it just within the last hours, we have a little bit of 2% increase in megawatts in the last hours. Inside this week, how many times we have a shortage versus the times we have a surplus on here. By day, in that last week, how many times was the decisions to buy a load versus when you produce and buy the shortages versus when you produce and sell the surplus. And again, the cost on here in the estimated net cost versus your full production cost and the predicted surplus and shortages throughout the time of that week. So this is just in general how that looks like. I can just do a very quick demonstration of what you can do. Again, like all of the materials that you're gonna see there is gonna be inside this PDF for creating this energy production. So we've already put together a kind of like a step-by-step process in how to put that dashboard together, assuming you have a superset going on. So in this case, anytime you start with a superset instance, you always need to connect it with a data source. So the nice part about Digital Hub is that whenever you launch up the superset from a project, that default database that connects to your project database is already there. So you can skip the step. But in other cases, you're gonna have to connect it with other databases. And then when you're building charts, you will first need to define the tables. So then after you have ingested those tables into your database, you just have to simply come into the table sections here and tell Superset what are the schema and what is the table name that it needs to look into. And then once you have all those tables that is already ingested and Superset knows what those tables are, then you can simply go ahead and just click on new. In here, you can either do a SQL query on the tables inside your database, you can build a chart, or you can build a dashboard. So in this case, I'm just gonna go in and build a chart on here. again, the first thing that you do is select a data source, which would be the tables that you have already defined for the superset. So in this case, let's say I'm doing market predictions. I'm going to try to build that first chart with the pie charts on here and just simply create that chart. If you've seen, was quick enough to see, there is a whole selection of different charts that you can select with superset and building on top of to make very nice visualizations. In this case, I'm going to take up my time filter. And then I'm going to do a count on my surplus versus shortage. Just gonna do a count. And explore different options and see what they get back. And then just simply run the query. So in this case, we already see there's a shortage on here. Doesn't look that well. So it's doing count instead of count distinct. Yes, that looks a little bit more correct. So now just with a few clicks here and there and choosing the metrics and the variables that you want, I can get my pie chart on here. You can do a little bit of more customizations. I like it look more like a donut or versus not. You can show the labels, not show the labels, put in a legend, so on and so forth. But you can choose this color scheme that you like. So in how you do here, and then once you have gotten the chart that you like, you can save it. So I'm gonna call this my surplus chart, surplus pie chart. And right now I'm going to add it to a new dashboard. So in this case, I can create a dashboard in here. This is my PyData. Save, and I'm gonna go to the dashboard. So you can see that it's here. And then as you have built in more charts and more charts, you can go ahead and edit the dashboard. In this case, then you can start with rearranging and dragging, adding in new charts in here, going through a bit of customizations anywhere throughout the dashboard on here. And that's kind of just how you work it on Superset. But eventually this is, again, going through the whole context in here for the workshop, the business context. We spend a lot of time on building the model itself. That is the machine learning process and the data science process itself. Those are all the technical work that have to go in to give you the best result for the solution and the problem. But eventually what is going to make sense to your business partner is what they see on the dashboard in here, what is going to give them that visual impact. And then for them to see, oh, I can save millions of dollars if I just go with the solutions. Again, you can see that like inside throughout this notebook, it was a fairly simple problem. We're just doing predictions on the electricity. We apply a fairly simple market logic engine on it to come up with the recommendation sections. These are things, of course, it can get a lot more complicated as you try to make things more accurate, suit better to your customers, to the enterprise need. But eventually, again, going back to that point, it doesn't have to be a complex problem for you to start off something. So a lot of time what we see failures in is when we go into a consultant and we have a business partner, they have this very big grand scheme of what they want to solve, but they don't give you enough time or efforts, or they're not willing to spend that much time and efforts for you to see that result on that grand scheme. So what you have to prove to them is that you can take a small part of that grand scheme, show them the value of what you can do, and then eventually when they're convinced, then you can start building out on that grand scheme. So that is, I guess, like just some business insights as things that I have learned when I was working on data science consultant projects with these oil and gas clients, and also throughout when we were building Digital Hub for the data science and clicking into what were the enterprise needs whenever we talk about data science in the business context. So we can't stay along in a little data science, technical computer science world. It's often very important in how you can communicate your values to people who doesn't understand data science, doesn't understand machine learning, and for them to see the value of what you can do. So I think that actually wraps up the entire webinar series on here. If there are any more questions, or I guess we'll have about 10 more minutes right now for any sort of discussions or questions that we can and answers here.
Okay, there is one. Do you run into cases that businesses wanted to see the model results from?
To see the model results from.
Yes,
So
hi.
Hi, yeah.
Yeah, hi, this is Sheila. So I work a lot, into this type of hybrid environment where, the business is not as knowledgeable as data science, right? And the type of tools and models that we use. And sometimes, they go the extra step and say, hey, show me the results from the model and tell me, why you decided to select that model. So, wanted to see, what was your experience, at least on the energy industry, about what will be some type of the results, that you're going to show them? Are you going to go more into precision? Will you be leading them more towards accuracy and, how to make it like that business friendly?
Right. Actually, I do have an answer with that. So like from our past experience, what actually gave us the best success was that throughout our entire process of building that model and building the solution, there is one subject matter expert that we will always go to, and we're in constant communication with that subject matter expert as we're building the solutions. So then like whenever you made a milestone on the solution itself, it's often very important to communicate how that works to that subject matter expert. And then that subject matter expert, they also have insights on their own. Maybe sometimes like they'll say, oh, the accuracy, we don't want that. We want something like false positive or false negative, right? Because like that's going to be what's going to be the critical metrics to them in terms of the performance. So then that communication is what I found to be very critical. So it's not like you end communication from the very beginning after you have completed that whole process of hashing out the objectives, but throughout that model building process as well, it's very important to talk with that subject matter experts. And they can also provide you with a lot of support along the way as well. So we had cases where after we got to a certain point of the model building, the subject matter expert believed that it was good enough of a MVP, or minimal viable product, and they were happy with it, that they already wanted to see it being deployed. So that it was way before planned, but then that subject matter expert got us connected with the IT department. So then like from there, we already started having discussions on, we have this model here, these are our requirements, what does the IT infrastructure looks like, what are the things that we would have to do at that point without the solution being completely mature. So there was still a lot of rooms for adjustments and modifications for us to be able to make our solution work best customized for that clients that we had. So no, that answers the question, but like in terms of, yes, we had seen places where the client comes in and say, why does your model work that way? And sometimes you may be able to answer that with maybe the machine learning model that you use actually give you back metrics on what are the most important features. Then like that is also like a good point to say, this is the machine learning model we use, and this is what it shows us being the most important features that leads us to test predictions. And sometimes they will see that importance of features of like, oh, that makes sense, or oh, that's unexpected, right? And then it goes off from there. But if you're using a little bit more of solutions like deep learning, where things are a little bit more black box, then that is where if you had that communication with the subject matter experts and they have a slight idea of what your solution looks like, they can help a lot at that point in terms of explaining that to their colleagues and to their managers and to the decision makers. So again, it's a two-way process in terms of success on their side and on your side. So that very constant communication is what I found is the key.
Thank you so much, Sylvia. That actually answered my question.
If there's no other questions, again, thanks for coming to the workshop. I hope that you find it helpful in any sort of way. Feel free to Slack me or like go on the channel, look for the links to the notebook. I also have the link there to Digital Hub. If you're interested to learn a little bit more there, you can also contact us if you want to see a demo of Digital Hub or not. But yeah, I would love to hear from you guys and see what you thought of the workshop.
Well, thank you very much, Sylvia, for your time and your presentation. It was really interesting. So thank you everyone, and have a good time.
Thanks for coming.
Bye.